Thank you for the introduction, Academic Jansky.
You're welcome. The speaker today, this is Hristo. His talk is example of non-reduced components and the Hilbert scheme of smooth projective curves using closed surfaces. Please.
Thank you, Academic Jansky. The topic today you just heard, and you can also see it on the first slide. I would like to say this is a work that is based on a joint paper with Young-Wook Choi and Sonja Kim from Korea. The presentation will give first introduction to the topic, then I'll briefly talk about non-reduced components of the Hilbert scheme IDGR, and then I'll explain the proof of the main results in the paper. Many people here have listened to several talks of me given here at the Institute of Mathematics on the Hilbert scheme of curves. But since there are always some newcomers to the seminar, I'm going to repeat some of the basic definitions that I'm going to use here. First, by curve, I mean a smooth, reduced, irreducible, complex projective algebraic scheme of dimension 1 and genus G. What we are interested are the embeddings of such a curve in the projective space of dimension R as a curve of degree D. And these embeddings are in fact parameterized by the so-called Hilbert scheme that I denote here by HDGR, which represents the contravariant functor that you see here. Let's ask me recently about the construction of this object HDGR, but I would like to say that this is a question that deserves a separate answer in the form of at least one such a lecture, and I practically have no chance of explaining what it is. So for this reason, I'm going to just some brief description of the properties of HDGR. HDGR decomposes into three basic types of components. Ones that I call regular, they're denoted here by R1 and so on. Then another type of components, S1, S2, and so on. And a third type of components like P1, P2, and so on. The main characterization of the components of the third type is that they do not have points that correspond to smooth integral curves. For this reason, usually one gets to focus on the union of the first two types of components, namely the R components and the S components. I would like to mention that a general point of the components of the first type represents a smooth integral curve, just like the general points of the components of the second type. But there is one significant difference, and it is that the components of the first type are generically smooth and of the minimum possible dimension, while the components that are denoted here like S1, S2, and so on, they have either dimension that is bigger than the minimal possible dimension or that they're non-reduced. And the story that I'm going to tell, in fact, has been more or less inspired by a conjecture made in 1921 by Francesco Severi, who claimed that if D is greater or equal than G plus R, then IDGR has only one component, essentially. Now, this claim made by Severi has been proven for the cases 3 and 4 and shown to be incorrect for R greater or equal than 6 by Lorenzine in 84-85. And similarly, Channel Kim has given a proof by different methods of the conjecture. and also given examples that it is incorrect for larger values of R. I was introduced into this topic by Hristo Iliev about 20 years ago, and back there I read the following results in this sequence. I read first the result of Lorenzine, then the one of Hristo Iliev, and then finally the one of Mazzetti and Sechiero. But to summarize what I found for the case R greater or equal than 5 is that first of all, if d is greater than this number that you see here, 2 times 1 minus 3 divided by R plus 2 times G is missing, by the way, here, plus 1 plus 2 divided by R plus 2, then IDGR is irreducible. Then Hristo Iliev found that this bound here for the irreducibility can in fact be improved. That is, we can claim irreducibility in the general case, R greater or equal than 5, for smaller values of d. Then it appears like this inequality here. And then she found also that if d is between this number here, 2r minus 8 divided by r plus 1 times g plus 2r plus 26 divided by r plus 1, and the number that I just mentioned, then IDGR is irreducible if and only if this number 2g minus 2 minus d is not divisible by 3. While in the other cases, it's reducible. There are components that parameterize curves that are triple coverings of other curves. As I said, after reading the paper of Hristo Iliev, then I found a paper of Mazzetti and Sechiero, in which paper they constructed a family of m-secant curves for m greater or equal than 3, which in fact provides another component in addition to the so-called principal component or distinguished component of the Hilbert scheme. And it turned out that such families of curves exist for this exact number that appears here in the first claim of Hristo Iliev, namely this number, 2 times 1 minus 3 divided by r plus 1 and so on. Although that their number was written in a very cryptic way. So it's not explicit by any means. In other words, they found a component that was generically smooth as long as d is smaller than those numbers, and it's a triple covering. So I can summarize the known results as of 2013, 2014, as on this picture here. I believe that I have shown this picture at our seminar some years ago. And essentially, they summarize the results that I mentioned already, plus some additional results. So here is this bound that I mentioned, found by Hristo Iliev, and there are some other numbers here. So for example, at the 4 and at the 3, identify a range. If we think of G and R as fixed and trace the components of the Hilbert scheme as d decreases from this number at the 3, and then we have this picture that I just described. Then when we initiated our study on this topic, we formulated several questions that are of interest to us. So first of all, we wanted to characterize the additional components of IDGR when d is smaller than the number found by Hristo Iliev. In particular, what we wanted to see is whether there are components that parameterize curves that are multiple coverings of irrational curves. And because all the known additional components of the Hilbert scheme were found for triple coverings, we asked whether there are components that parameterize curves that are double covers. And indeed, some other questions, including whether there are additional regular components in the case of the so-called Brunner number being non-negative, as in this case, the scheme has the so-called distinguished component, which dominates the modular space, and some additional questions. Our first result joint result on this topic with Yongguk Choi and Sonja Kim was published in 2017, and it contains two main claims. So the first claim that we produced back then was about the existence of a component that parameterizes curves that are double covers. And the result sounds as this. So if d is between a number that I have here just denoted like eta 5, I can make this more specific if I have to, and another number that you see here on the right, then IDGR has an additional component in addition to the distinguished one. And the points of this component are in fact curves that are double covers of curves of genus gamma, provided indeed that these numerical conditions that I have here are satisfied. And further, the curves that we have in PR, they're in fact embedded by subseries of the complete linear series, which is the canonical divisor on the curve C times the line bundle that is pulled back of the canonical divisor on the base curve in gamma. So this was the first result, and one more similar to this one, which in fact makes slightly different assumptions about D and G, namely if, like the previous case, 2G plus 2 minus D divided by 4 is a not integer, we have 2G plus 1 minus D divided by 4 being a not integer. Then a little change here in the assumption about D here. And then we again have such a component that I denote here by D prime, in addition to the distinguished one. Again, the general points of this component are double covers of curves of genus gamma, but this time the embedding that we have in the projective space of dimension PR is given not by the ramification divisor of the double covering, but in fact the ramification divisor of the double covering minus omega. If you indeed recognize this product here, omega c times the pullback of the inverse of the canonical divisor of the base curve as the line bundle induced by the ramification divisor. For a general point, or arbitrary point, in fact, on the curve C. So these are, in fact, important results because they provided sort of claims that we would extend later, as you will see. So the extension of the first result that I quoted is the following theorem that I call theorem A. And in theorem A, in fact, we gave a very clear geometric description of the curves that make the first component D in the results that I mentioned, as we have much milder assumptions about the invariance D, G, and gamma. Namely, we have D to be equal to this number here, and R to be between the maximum of gamma and 2G minus 1 divided by gamma, and G minus 3 gamma plus 2. As we get a description of that first component D as now generically smooth components, which means that the dimension of a tangent space is equal to the dimension of the component. We calculate just as before its dimension, and then we have the geometric description of the curves that make this component as follows. In the extreme case, when r is equal to this number here on the right, g minus 3 gamma plus 2, then the curves are in fact cut off on a cone by a general quadratic hypersurface, and further on, the curves that we have there are again induced by, you may say, the embeddings are again induced, you may say, by the ramification divisor, r phi of the covering of x to the hyperplane section of the cone. And in the case when r is smaller than this number that I denote here by capital R, then the curves parameterized by the component are just general projections to general hypersurface of dimension R, subspace of dimension R. The importance of this result is that, or perhaps I should visualize first. This is what the results say visually. So we have here a cone. So this is the cone over some curve y. It is of genus gamma embedded by a line bundle of degree g minus 2 gamma plus 1 into this space p r minus 1, which is in fact p of dimension g minus 3 gamma plus 1. Here and then we have the cone over this curve, and the curves from the family that I described here are just cut on the cone by general hypersurfaces of degree 2. And to say two important corollaries from this result. This result is important because it has to do with, in some sense, has to do with the Severus conjecture. Namely, the result gives the following two corollaries. First of all, we have the one that is my favorite, that for specific values of R, we get that the Hilbert Scheme IDGR gets a second regular component, in addition to the so-called distinguished one that I have discussed at other lectures here of the seminar. And it happens, for instance, if you take gamma equals 9, g equals 46, d equals 58, r equals 10, and then we have this Hilbert Scheme here that has two regular components. And another important corollary is that this Hilbert Scheme IDGR gets two different generically smooth components parameterizing linearly normal curves, which is in fact a statement that has to do with the so-called modified Severus conjecture. Okay, so one of these components is the component of quadruple covers that is obtained by Sahara and Mazzetti, and the other one is our component. I just want to mention that in this case, the denominator number is negative. So there are some other modified Severus conjectures that need additional work. So this corollary is not a contradiction to that. And now let me say a little something about the non-reduced components of IDGR. So to this point, we discussed the result in theorem A, which talks about generically smooth component, which means that it is not non-reduced. It is generically reduced, you may say. The first such component, non-reduced component of IDGR, has been given by Mumford in 1968 in his famous paper on pathologies. And then other examples of non-reduced components of IDGR are equivalently abstracted space curves, have been given by Grousson and Peskin in the late 70s, early 80s, then by Cernesi in 1981, which is a very nice example that I really like, and then some other examples by Walter, Boulon-Declercq, Miroir, Nassau in 2006, and Hirokazu Nasu in 2006, and also a relatively recent result by Ananyu Dan, 2017. All of those examples that I mentioned here, they concern the case R equals 3, or as I said, space curves. In fact, the only example that exists to our knowledge of non-reduced components of IDGR in the case R greater or equal than 4 is the one that is given by Chiliberto, Lopez, and Miranda in a paper from 1994. Here is our motivation, in fact, to try to find non-reduced components. So on one hand, there is only one such example for R greater or equal than 4. On another hand, the superabundant components, they can be non-reduced ones, or they can be generically smooth, but of dimension greater than the expected one. However, it is far more difficult to identify non-reduced components, especially when R is greater or equal than 3, as I said, and in a way they're more interesting. The way one obtains or shows that a component is generically smooth is usually to find a family of some dimension and then try to calculate the dimension of the tangent space. And if it happens that the dimension of the tangent space is equal to the dimension of the family, then you have a generically smooth component. With the non-reduced components, the situation is that the dimension of the tangent space must be bigger than the dimension of the family, but one is never sure, or a priori at least, whether there isn't another family which contains properly the given one, and in this way it could possibly be a generically smooth component that contains the family of curves properly. And as I have put here in the last item here, one can compare this equation with what Tolstoy writes in Anna Karenina. All happy families are alike, each unhappy family is unhappy in its own way. In other words, generically smooth components are smooth in the same way, unlike the non-reduced components, which can be non-reduced in different ways, so to say. Then here is the result that we have about non-reduced components. It in fact generalizes to some extent in one of the cases the result that we have published in 2017 about the component D prime. So the result is this. So assume gamma to be greater or equal than 7, G to be greater than equal than 6 gamma plus 5, and fix these integers in the following way. D is to G minus 4 gamma plus 2, R is G minus 3 gamma plus 2. And then the claim is that I D minus 1, GR minus 1 has a non-reduced component, D prime, D minus 1, GR minus 1, such that the dimension of this component is the expected dimension plus this number. At the general point of this component, we have the dimension of the tangent space is 1 bigger than the dimension of the component. And then we have the geometric description of the curves that correspond to such components. Namely, they again lie on cones, but now they pass through the vertex of the cone, and a projection from the vertex of the cone to a hyperplane section of the cone induces a morphism of degree 2, as the line bundle embedding x prime in this projective space PR minus 1 is again given by the ramification divisor minus a point P on the curve x prime, just like in the theorem about the component d prime from 2017. Now, what we have here are curves that are double coverings. So both the components that I started with, d and d prime, they're parameterizing curves that are double covers of other curves. Such curves that are double covers, they in fact can be found on cones. And that's what we have been led to consider. And further on, as we have been trying to understand better the components d and d prime that I started with, we look at the embeddings that we discussed about them, and we observe that the difference is that the curves that correspond to the component d, they're embedded by a line bundle of such curve that is double covering of another curve, while those that correspond to d prime are embedded by a line bundle minus a point. But what's the difference between the two is that the second embedding, the one given by the linear system L minus x here, is in fact the so-called inner projection of the first one to a codimensional subspace of the projective space. And that's the situation, in fact, with the first two theorems. So here I have the embeddings, omega c times the pullback of the inverse of the canonical divisor for those in D, and the pullback of the canonical divisor times the pullback of the inverse of the canonical divisor minus a point. Then here is how we get to visualize this thing. So this is in fact the motivation for the construction that I described in theorem B. So if one starts with the components as from theorem A, then we have curves that are cut on a cone by a hypersurface of degree 2. So here is this blue curve that I denote here by x. And then if I take a point x on this curve and consider the linear projection with center x to a codimension 1 subspace, linear subspace of PR that I denote by H, we can observe that first of all, this this inner projection that I have here extends in fact to a morphism of the curve X and its image. So I start here with such a linear projection to a hypersurface in PR, and it's easy to see that it extends in fact to a morphism. And further on, if you think of a line that passes through X and another point on the cone and hits the hyper plane H, then you can also visualize the image of the cone F that I have here. So for example, if you look at the ruling that I have here through the point X and sorry, is there a question? Is there a question? I assume not. So if you look at...
No, I don't think so.
Okay, thanks. So if you look at the image of this line from the ruling of the cone, the green one, then its image is a point. But all the other points, so all the other points, they have they can also be mapped in such a way that one gets to see that the image of this cone F is in fact another cone that I have here, F prime, for example. And further, if you look at this curve that I have here, X, since all points along this line from the ruling, in fact, are collapsed to a single point, which is in fact the vertex of the cone f prime, you can observe that this second point of the intersection of the green line, in fact, gets mapped to this vertex that I have right here. So, in other words, the blue curve that I have here on this cone under the linear projection, in fact, gets mapped to a curve that I have denoted here like x prime that passes through the vertex of the cone. And the hyperplane sections of the cone, like for example y that pass through the point x, they're mapped to hyperplane sections of the cone f prime. Okay, so that's the motivation for the construction that I have here. So here we have a geometric motivation that I'm going to make algebraic soon. Before proceeding with this, with the algebraic construction, I want to say a few words about multiple coverings of curves. So if we consider a curve that is a M to 1 cover of another curve, and phi is the morphism, the covering morphism, then we have this exact sequence that I have here. So I have the structure sheaf of the base to be mapped to the push forward of the structure sheaf of the covering curve C, and then we have the co-kernel to be the so-called Chernhausen module. So the Chernhausen module is in fact a vector bundle of rank n-1, and it splits as this. Actually, the push forward splits as direct sum of the structure sheaf and the Chernhausen module. And because the Chernhausen module is of rank n-1, in the case of m equals 2, it should be just a line bundle. It's a line bundle, and it's easy to compute, in fact, that it's a line bundle that is of degree minus g plus 2 gamma minus 1. In fact, it's not difficult to say this. In fact, this indicates how we can proceed with the construction of the algebraic constructions that I more or less visualized here. So the idea is to look for our curves on cones. And in particular, if one starts with such a double covering, then one can look at the rank 2 vector bundle O gamma plus O gamma V, where E is the divisor, is a divisor of this degree on the base curve gamma. Then the projectivization of this vector bundle will be so-called root surface that I denote here by S. And such a root surface S, it has two canonically determined sections. So because the push forward that I have splits in this way, we can have either this exact sequence or the other one that you see here. So the first exact sequence by the theory of root surfaces correspond to so-called section of minimal self-intersection denoted gamma naught, and another one that is denoted here by gamma 1. The second exact sequence is the section that is denoted here by gamma 1. Further on, let me mention a few things about root surfaces. The Picard group of the root surface is generated by gamma naught and the pullbacks of the divisors on gamma. We have further on that the self-intersection number of this decomposable root surface gives about gamma naught, that it is equal to minus g plus 2 gamma minus 1, and the intersection self-intersection number of gamma 1 is equal to g minus 2 gamma plus 1, because we have such a relation between the two sections. And one can go on and compute, for example, the dimension of some linear series on S. And when we compute it, this dimension, it turned out that it is equal to G minus 3 gamma plus 3, which is exactly R plus 1. Then I figured out that I should be looking for those curves on the root surface in the appropriate divisor classes. It turned out that I can look at the linear series essentially induced by gamma 1, or equivalently gamma naught plus EF. So this is the pullback on F on S through F of the divisor E on gamma. And this linear series is base point free and defines a morphism from S to PR, projective space of dimension R, as it collapses the section of minimal self-intersection to a point, which is just the vertex of the cone. And further on, we have some, indeed, other hints. As I said, by looking at the curves in different classes, it turned out that the curve that is in the class of 2 gamma naught plus 2 EF has image on the cone that has the right invariance. So that in fact turns out to be our curve. Now, why I'm saying all those things that are related to TRMA, the reason is that I need, in fact, those things in order to describe the algebraic construction of the curves that are parameterized by the component in TRM-B. Before going there, I just want to mention that the proof of TRM-A essentially goes as this. One considers scroll F over a curve Y of genus gamma such that this curve Y has genus gamma and is embedded into PR by a line bundle of degree G minus 2 gamma plus 1 by some, again, well-known facts about rule surfaces and scrolls. Such scroll is necessarily a cone, so it is necessarily a cone. And then by taking the degree 2 hypersurface, or rather its intersection with the cone, we get the curves from our family X. And then one proceeds with the proof of theorem A by counting the curves from the dimension of such a family and computation of the space of global sections of the normal bundle to such a curve X. And it turns out that it has exactly the same dimension. Indeed, in general, this is a very difficult thing to compute. But because our curves are on cones, it is somewhat easier. Now, I have this result about curves and cones that I'm going to skip because I don't have that much time, although it's important, sort of. And we now go to the outline of the proof of theorem B. I said that I'm going to construct them algebraically. And then I have to proceed further to show that the family, in fact, gives rise to a non-reduced component. So each such proof has these two parts. We construct the family, then we show that the family is a component, and then we would need also to show that this component is non-reduced if we are aiming non-reducibility, which is done by comparing the dimension of the maximum possible component that contains such a family with the dimension of a tangent space. For this reason, the proof is done in 3 steps. So in step 1, we construct the family F prime of curves that satisfy these conditions that I have in item 2 of the family. Okay, I said, namely I'm going to find them on cons, but I'll do this algebraically. And then we get to compute also dimension. Okay, so let's revert to the steps. So we get to construct such curves. Then we get to consider the closure in the scheme ID-1 GR-1 in of the set that parameterizes this family. It will have the same dimension as the family f prime here, and I get to show that the dimension of this family is exactly this number, 2g minus gamma minus 1 plus r squared. That's step 1. In step 2, I get to compute the dimension of the tangent space of such a family, or equivalently, the dimension of the space of global sections to such a general curve from the family. And in the third step, which is not an easy, it's quite difficult oftentimes, we get to show that this closure that I denoted here like d prime is not contained properly in another component. In other words, it is really a component. And because the dimension of the tangent space, as in step 2, is bigger than the dimension of the family, it makes a non-reduced component. Non-reduced component. Now, let's get to the steps that I outlined. I'm going to recall a few basic facts here, or facts from the setup that I'm going to use, and then I'll show you a picture that will clarify what we are doing, in fact. What we get to consider is general curve of genus gamma. Then I get to consider a divisor of degree g minus 2 gamma on the curve. I take a point on the curve, and I also denote the divisor that is the sum of phi prime and q by e. So notice that this is a divisor of degree g minus 2 gamma plus 1. Then let's consider the following ruled surfaces. S prime, which is the projectivization of this rank 2 vector bundle. So the structure sheaf plus the structure sheaf twisted with minus e prime. That will be S prime. And also the ruled surface S, which is the projectivization of O gamma, O plus O gamma twisted by minus E prime minus Q. So I'm looking at those two ruled surfaces. And as we'll see, those ruled surfaces are connected, in fact. What we have on the first ruled surface is I have a section of minimal self-intersection that I denote like gamma prime. On the second one, I have the section gamma naught. In fact, this is the one that we had in theorem A. And of course, we proceed further to mention that once again, Picard group of the ruled surface is generated by those sections of minimal self-intersection and the pullbacks of the divisors on gamma. As it is standard, I get to denote the divisors that comes pullbacks from gamma, like the divisor times the corresponding fiber. So I have divisors like df prime on s prime and df on s. And the key thing is that the two ruled surfaces that I just described, they are elementary transformations of one another. What does this mean? So here is the picture that gets essentially to clarify the situation. So the first ruled surface, as that I have here, has this section of minimal self-intersection, gamma naught. It is unique. And similarly, the second surface, S prime, it has this section of minimal self-intersection, gamma prime naught. Then I have that S prime can be obtained from S in the following way. So if I take a point X in the fiber QF, this means it projects with the natural projection down to Q on gamma and blow up S to get this picture that you see here. So you can think, I haven't drawn the other fibers, but there are other fibers here that are not affected in this transformation. So I have the proper transformation of the green fiber plus the exceptional divisor that come from blowing up the point X. So I get this blow up, and then I contract the proper transformation, the strict transformation of the fiber QF to a point. I get, in fact, nothing but the surface S prime. So it has to do with both surfaces S and S prime being decomposable, because row surfaces can possibly be decomposable for certain ranges of the so-called E invariant. So it has, but if it is like we have in our case, the E invariant bigger than 2 gamma minus 2, then they're definitely decomposable. So anyhow, so what I have is that the first row surface blown at X, and then having its fiber contracted, gives us S prime here. Then this is the so-called elementary transformation of the row surface S at the point X. Conversely, if you take the fiber QF prime over the point Q, it has a unique intersection point with the section of minimal self-intersection gamma prime naught. And that's, in fact, that I get to consider for the inverse transformation. So if I blow up this point, so I'm going to get back this picture. So this green dot, sort of, you may say, naively, gets transformed to this green line here, this fiber, while this orange fiber is the one that you see here. And then I can blow down this orange line here, and I get the point, in fact, on the fiber QF. So it gives, in turn, the root surface S. So the inverse transformation that I described is denoted like elementary transformation of the root surface S prime at the point X prime. And further on, what is our curve X? So our curve X that I considered in the beginning, so if you recall here, the curve that is here in blue. So here is the curve that's here in blue, okay? And here is the curve X prime that I got by its projection on the cone F prime. Can be seen as images of the curve C here, you see here in blue, then C prime that you see here in blue again on the root surface S prime. Now, this curve that I have here is in the linear series 2 gamma naught plus 2 EF. And its image by what we have in theorem A is exactly cut on the cone F by a degree 2 hyper surface. This one that I see here, that you see here, is in fact, if you consider similar morphism of the root surface S prime to projective space PR-1, it will turn out, will be a curve that must pass through the vertex of the cone, because the corresponding morphism collapses gamma prime naught to a point. So this gets collapsed to a point, and in turn, the curve must pass through the vertex. Now, let me just go through the proof further on. So these are in fact the things that I more or less described. So we can look at morphism psi prime that's going to take S prime to projective space PR-1. It is induced by the linear series gamma prime naught plus E prime F prime on S prime. So it maps S prime to con over a curve of genus gamma and degree D minus degree G minus 2 gamma. As I said, X prime passes through the vertex. And more importantly, we can count or we can compute the dimension of the family of such curves that we find on the cone F prime. How does the computation go? So if I denote by F prime the family of curves that are the images of the divisors from this linear series. So this is the linear series that is induced by C prime, and it is 2 gamma prime naught plus 2 times C prime plus Q F prime. Notice that such a linear series has a base point exactly S prime. So this is the point where the fiber QF prime intersects gamma prime naught. But the general elements of the linear series are smooth integral curves of genus G. So these divisors are sent by the morphism psi prime onto the cone F prime by psi prime as they pass through the vertex, and they have the right invariants. And then how do we compute the dimension of the family? We get to account the parameters on which this construction depends. So first of all, we get to compute the number of curves, number of parameters for the curves gamma. And this is well known to be just 3 gamma minus 3. Then I have to account the number of parameters that allow me to choose the line bundle O gamma of E prime. So the one that gives the root surface S prime essentially. And because this number is much bigger than 2 gamma minus 2, we have that number of parameters should be gamma, just the dimension of the Jacobian of gamma. Then we have number of automorphisms of the projective space PR minus 1, and we have R square minus 1 such. Then we have one more parameter to choose the point gamma, because it also takes part in the calculation. And further on, I have to subtract the subgroup of automorphisms of PR minus 1 that fixes the scroll F prime. And then finally, I have to compute the dimension of the linear series from which I choose the divisors. Okay, that's how I compute the dimension of the family F prime. And the computation of the family gives me this number for the dimension of the family. It is 2G minus gamma minus 1 plus R squared as here. As I said, D prime to be the closure in ID minus 1, GR minus 1 of the set that parameterizes the family F prime. Okay. And what we further get to do is we want to see explicitly the relation between the curves from the family F from theorem A and the curves from the family F prime from theorem B. So the relation is that, like I started with the motivation, the curves from the family F prime can be seen as inner projections of the curves from the family F. Okay, so here is the picture with the curves from the different families. So in PR, I have the cone F, and I have the curve X Now it is a double covering. It is a double covering of the hyperplane section. An inner projection from X, in fact, sends the cone F to a cone F prime, but in projective spaces codimension 1. And of course, this cone can be seen as the image of the morphism psi, while this cone F prime can be seen as the image of the morphism psi prime of S prime. And of course, we have the relation with the elementary transformations between S and S prime. Okay, so this is how we can visualize the geometry that goes on here. So this is the construction of the family. So the next step, as I said in the outline of the proof, is the computation of the dimension of the tangent space. Or in other words, it is the computation of the space of the global sections of the normal bundle of X prime in PR-1. So for this calculation, we use the following proposition that I have put on the slide. The proposition says the following. If C is a smooth integral curve in PR, where R is at least 3 and H is a hyperplane in PR, and if we fix a point X on the curve and consider inner projection of the curve C to the hyperplane H with center X, and if the image is a non-degenerate smooth curve in PR-1, then we have this exact sequence. So what I have in the exact sequence are the normal bundle of the curve C, and also pullback of the normal bundle of the base curve twisted with the point X here. Then I have one more term here in the beginning that has to do with the ramification divisor and also twist by hyperplane section here. I need such a sequence in order to compute H0 of the normal bundle of X prime. So that's why I need such a sequence. So, we have used such a tool, in fact, in the proof of theorem A, but back there, the projection wasn't inner, projection was general. So we don't get to, and also some other stuff. We don't get to use the tool that is from the proof of theorem A. So we needed a different one. And it turned out to be a little bit complicated to some point. Later on, we figured it out. Now, if we have this proposition, then we get to apply the proposition to the double covering morphism X prime to Y prime. So to recall the standard the picture that we saw, I get to apply the proposition to the morphism phi prime, which gives me a double covering X prime to the hyperplane section of the cone F prime. So it's a double covering. So you can see it, for example, a projection from the vertex of the cone F prime, for example. So it's a double. You can see it from the ruling of the cone, or from the construction that comes with the morphism psi prime. So we get to apply it to this morphism, and then the exact sequence transforms into this one that I have right here. Now I can compute H0 of Nx prime because it is exact on the global sections. It's exact on the global sections because of the degree of this line bundle on X prime. It is bigger than 2g minus 2 gamma, for which reason we have it exact on the global sections. And then we can compute this one, the global sections of this line bundle by Riemann-Roch. And then we also need to compute the space of global sections of this line bundle. For its computation, we need to use that the push forwards of the structure sheaf of x prime twisted by p prime through phi prime splits in this way. And then the computation of h0 of phi prime pullback of ny prime twisted by this point can be calculated from here essentially, and we can and we obtain from the exactness on the global sections of the sequence that h0 of nx prime is in fact equal to r squared plus 2g minus gamma. Notice that this number is one bigger than the dimension of the family. So we computed the dimension of the tangent space, and we computed the dimension of the tangent of the family. Dimension of tangent space turned out to be one bigger than the dimension of the family. So we have, in other words, a candidate for a non-reduced component. So I want to mention once again, calculations of this kind, like dimension of space of global sections of the normal bundle are in general not easy, but we are kind of lucky that our curves are on cones and it makes it possible. Then we go to step 3. Step 3, as I mentioned, is the step in which we get to show that this closure that I denote like d prime is not contained properly in a component. So this is crucial. And for this, I'm just going to mention how the proof goes further without giving any details. So for this one gets to assume the opposite. In particular, one assumes that d prime is contained properly in another component like E, for example. This means that the dimension of E is greater recall than the dimension of F plus 1 at least, possibly more. So in particular, it must be equal to r squared plus 2g minus gamma. However, using Hilbert semi-continuity, we get that this component E must have dimension exactly equal to r squared plus 2g minus gamma, and it must be also generically smooth. So if there is a component E that contains properly our closure d prime here, it must be generically smooth and of dimension exactly equal to r squared plus 2g minus gamma. The essence of the argument that follows, which I'm not going to explain, is that the gonality of the curves of the family f prime is too large in order for such a family f prime to contain properly, to be contained properly in a component like E. And I'll stop at this point. So that's the essence of the argument that follows. So I just want to bring back the picture that I had from the beginning and just mention that it fits into things that we found later about the components of the Hilbert scheme and its generic smoothness and non-reducedness and sample properties. So I'll stop here.
Thank you, speaker. Do you have any questions or comments? If there are no questions, let's take the speaker once again.
May I ask question?
Sure.
May I ask question? Yes.
Yes, you can ask.
Please, thank you very much for your interesting talk. And please, over what fields do you consider algebraic curves? Over what field?
C. My curves are
over complex numbers. Yes.
Over complex numbers, yes. So all curves that I consider are over C.
Thank you. And my question is follows. As you have a non-reduced component of the Hilbert scheme, this component contains nilpotent elements. Yes?
Yes, yes.
And what the image of these nilpotent elements to the set of curves? You consider smooth curves, probably, yes?
Sorry, can you repeat the last part? Smooth cases?
You have nilpotent elements
Yes.
in a component of a Hilbert scheme.
Yes, yes, yes.
What images of these nilpotent elements in the set of curves?
Unfortunately, I cannot answer this question. So I do not know. So the nature of our proof cannot provide such an answer. So so our proof goes, as I said, by using some numerical constraints on the components that can possibly exist in this case, and we show that due to some numerical restrictions, the only ones that can exist in this case must be double covers of curves of genus gamma. I mean, curves that are double covers of genus gamma, but these are that we in fact construct. So I cannot give any clearer description on what let's say the nature of the singularities might be.
Thank you. Thank you.
Some other questions? Okay, if no questions, thank you very much once again for the talk.
Thank you.
And the next talk will be in September. We'll announce this in time.
So Mitko, you raised your hand.
So maybe it's time to stop the recording.